15 years ago, I took a sabbatical, and I spent most of that sabbatical kind of looking around at things around me and asking, can I make a camera out of that? Can I make a camera out of that? Can I make a camera? And I looked up at the moon, and I thought, can I make a camera out of that? And somehow this just stuck with me. This infected me like a virus for the time since then. And I really love this problem. Here's the idea. The Earth reflects light onto, there's the sun, there's the moon, there's the Earth. Sunlight hits the Earth, reflects back onto the moon, and you can see that in the picture of the moon there, that darker part is reflected, that's Earth shine. So the idea is, can we use a telescope on the Earth, look up at the moon, record data, compute on it, and come up with a picture of what the Earth looks like from the moon? Now, let me be the first to point out there's no scientific reason to do this. Okay? We've got satellites. They make beautiful high-resolution pictures of the Earth. We don't need this image. But I just really love the idea of doing that, and there's a science outreach reason to do it. Wouldn't it be cool if amateur astronomers from their backyard telescope could go and take a picture of the moon and reconstruct an image of the Earth from space? I think that would really just capture everyone's imagination. So that's the goal. And so I've been working on this for 15 years, not full-time, but part-time. And I've come up with a number of ways to do it. The spoiler alert, none of them really quite work yet, but I want to show you the best one. And that's by looking at craters around the edge of the moon. Okay, I need an extra hand. All right, so here's a crater. This is the near side of the crater to the Earth. This is the far side. It's somewhere around the edge of the moon, like you see there. Here's our proxy for the Earth reflecting light from the sun. And it's got some image on it. Here it's a real simple image, so you can see it in the back, just a red and a blue square. Now, this is not going to work. They're going to hate me for this. I'm going to go away from the lights so you can see it. This Earth shine hits the front edge of this crater and casts a shadow on the back edge of the crater, on the back face of the crater. And let's think for a minute about what that back face of the crater sees, okay? So transport yourself to the back face of this crater. What's it going to look like from that point of view? You're going to see the Earth creeping up, depending on exactly where you are on the crater, peeking up above the front side of the crater or not. And the amount of brightness that shines on you there at the back face of the crater is going to be the sum of all the light that peaks above the front side of the crater from the Earth. So you can imagine that if you carefully measure the brightness along that back part of the crater, you can pick out these integrals over the Earth's surface, these little slices of the circle. And you can pull out these sort of one-dimensional slices of what the Earth looks like from the moon. So that's a one-dimensional picture. And then if you do it from many different craters around the edge of the moon, you'll get lots of different orientations, and you can reconstruct a 2D picture of the Earth. So I've simulated that, and here's the result. Now, the bug is this, the fuzzy region of the shadow of the Earth shine on the crater is really small when you look at it from the Earth. And so, okay, so there's a picture of the Earth from NASA. The middle image is the best you could possibly expect with really good conditions and a really talented amateur astronomer doing this method to reconstruct the image of the Earth. It's not really worth it. If, on the other hand, you were to use a professional telescope, you could probably expect to do as well as the image on the right. But, of course, it's not worth getting time on a professional telescope to take an image like that. We have satellites. So that's where I am with it. But now here I want to make a plug for curiosity-driven scientific research. This problem you can repurpose and use it in a useful way here on the Earth. So here's the big reveal, okay? The manipulation that makes it happen. So this is the front side of the crater. If instead we take it from there and we put it like this, now you have pretty much the same optical elements. You've got the straight edge occlusion, you've got the plane that it's projected onto. But now, what is this? This is a corner. This is a building, and this is the ground plane next to it. Or this is a tree, and this is the ground next to it. And so this would let you look at the ground and see around it, just as you could use the other configuration and see the Earth from those shadows. Now, there are three big differences from the Moon project with the corner camera. One is, finally, we don't have to worry about resolution, because we're going to be close to this, so we have plenty of resolution. That's good. And they have two other things in the other direction. One is we just got this one edge, rather than for the Moon, we had that whole series of edges. And so it's only going to be able to make look at variations in intensity in one orientation, but not in two orientations. So it's going to be, if you will, a one-dimensional image. Intensity is a function of angle. And then there's a second difference, which is really kind of magical. With the Earth, we had this bright thing out in the middle of the darkness of space, and it had pretty good contrast when it shines on the Moon. With this Earthbound camera, we're going to have someone behind the corner that you're trying to see, and you want to know what is the difference in intensity falling on this ground when they're there and when they're not there. And just as an illustration of that, suppose Neil were to stand up right now. How much do you think that intensity on this piece of paper changed based on him standing up? Well, it's a pretty small amount. Thank you, Neil. It's a pretty small amount. It's about 1 part in 1,000 of the intensity from here. So here's our new application. We're going to use it to see around corners in buildings. And this 1 part in 1,000 is just a beautiful number. It's invisible to our eyes. We can't see it. But you can compute it with an ordinary image from an ordinary camera by averaging over the appropriate pixels. So it's like this magic leprechaun or magic fairy that's there all over these corners. There are these images being formed, and they're invisible to us. But if we take a picture and process them properly, we can pull out pictures of what's around the corner from them. So let me show you that in action. So there's our simulation showing that it's about 1 part in 1,000 is the intensity differences that we're looking for. So we're going to look at the ground here and try to see what's around the corner. Now, so there's our camera looking at the ground. Here are 2 people who were students at the time, Katie Bauman and Vicky Yee. Katie's now faculty at Caltech, and Vicky's now a grad student at Berkeley. They were in my lab at the time, though, and they worked on this project. So here they are walking around the corner, and that camera that you saw can't see them. And here's what the camera sees. This is the world's most boring video. I'm going to play it now. Here we go. No, sorry. Well, there's audio. The audio is a street sound. There we go. There, you can see it just playing. And invisible to us, there are 1 part in 1,000 intensity variations there, but we can capture them and compute them by taking averages of the appropriate pixels. Here are the pixels we should take averages over, these little pie-shaped things. The yellow you take positive, the blue you take negative, and you add them all together, and you can achieve this 1 part in 1,000 intensity resolution. And here's what you get. You get a picture of a one-dimensional picture of what's around the corner. So it's a plotted angle is going horizontally, and vertically is time. What can you see from a one-dimensional video? Well, you can count people. How many people are there? There are 2 people there. You can see these 2 tracks. You can see how fast they're moving. You can see if they're going toward or away from the corner. You can see quite a bit of important information for you as a pedestrian just by looking at these one-dimensional videos. Just to show you, there's a one-person video trace. So what might you use this for? Well, personal safety, it would just be nice to know if there's someone around the corner. Also, automotive safety. In an automobile, you'd like to have your car slow down if it thought there was a kid hidden behind the corner running toward the street that you can't see. This is a way you might be able to see it by, again, with a conventional camera, looking at the ground and seeing the child. So we wanted to do a feasibility study. Can we see a child with this thing? Now, a child is even harder to see than Neil because they're smaller and closer to the ground. And so we borrowed a child. There she is. And here, she's walking around the corner. We were behind the corner taking her video. Bottom left is the most boring video. And the reconstructed intensity as a function of angle is shown there at the right. And you can see we can reconstruct an image of the child around the corner. So what a cool transition it is from this crazy little scheme to take a picture of the Earth from space using the moon as a camera to something that actually might help your car slow down if it thinks there's a child around the corner. So score 1 for curiosity-driven research. Thank you. And these are my collaborators.